record on this computer. Now I'm going to share my iPad. All right, and away we go. All right, fantastic. Okay, so you can see my iPad, right? And you can see my face. And again, I emphasize that if you got any questions, probably what's going to happen, I'm going to spend most of my time staring at my iPad here, and I'm not going to keep much attention on what's happening on the screen. So if you got any questions, your best bet is just going to say, hey, professor, answer my question, and I'll say, okay. All right, so now, StatMech. That's what we're all here for. StatMech. All right, so now I feel like I should warn you. So again, this is probably something you're already aware of, but I just want to make it clear that, and this is the case with all of your classes, but things here are going to start out, I would say, almost insultingly slow. All right, so we're going to have to establish some initial groundwork so that we all understand the basics of what we're doing. And then it's just going to get more complicated from there. So the first few lectures, again, as I said, are probably going to be almost insultingly basic, but it's going to quickly snowball out of control. So I invite you to pay attention. All right, so what is StatMech? So allow me to illustrate what it is we're going to try to do with a relatively basic example. So let's imagine we have a box, okay? So here's a box. Okay, now we take this box and we fill it with some kind of gas. Gas. All right, so now we know from our everyday experience that if you take a gas and you seal it in some kind of container, that gas exhibits some properties that you can measure. All right, so for example, the gas, when you conceal it or when you hold it in a container, it's going to exert a pressure on the walls of the container. It's going to have some temperature, it's going to get hot or cold, depending on how much energy you put into it or take out of it. And moreover, this pressure and the temperature also depend upon the conditions of the gas. So for example, both of these things depend upon, for example, the volume of the container. So if you take the container and you make it bigger or you make it smaller, that is going to affect what the pressure and the temperature of the gas are. All right, so you guys probably all are familiar with the ideal gas equation, right? So the physics version of the ideal gas equation is this. Okay, so what this says is that the pressure and the volume of the gas depend, so this is the pressure, this is the volume. I'm sure you guys all know this. In here is the number of molecules of gas that we've got. K is Boltzmann's constant, which, we're advanced physicists here, so we don't care what numbers are, so I'm not going to tell you what the number is, because who cares? And T is the temperature.
Question, Dr. Tom.
Yes, please.
So if I recall correctly from 132, which I took a long time ago, we would abbreviate KBT to tau to be some sort of constant. Will we be doing that here or just leaving it as KBT? I
have to confess that I'm not familiar with that notation. So I think in general, I'm going to write it like this.
Okay.
You may, when I started my career, I started as like a biologist, God help me. So I may sometimes also write it down in the format that a biologist would be familiar with, which is this, PV equals nRT. So same thing here, R is ideal gas constant, and N, I believe, is the number of moles as opposed to the number of molecules. So when I write down the ideal gas law, I'll write it down either like this or like this. I'm not too familiar with this tau business. Okay?
It's just for units. Yeah.
Yeah, so again, it's going to be a very rare circumstance where we actually write down any kind of numbers or units. So, we're going to take the theoretical physicist approach here and say we just couldn't care less.
Okay.
All right.
Thank you.
Yes. All right, so this thing, this PV equals NKT, this is the ideal gas equation. And so this is what's referred to as an equation of state. Okay, and what this allows you to do is, given some parameters which describe your gas, this equation allows you to predict that if you do something to it, what is going to happen, right? So if I have a gas that's in a given state and I change the volume of the container, then something's going to happen to the pressure and the volume and the temperature. And this equation allows me to predict what's going to happen. All right, so now the thing to recognize about this arrangement is that what we're looking at here is a very macroscopic view of things, all right? So this is the kind of view of a gas that we have as large macroscopic people making measurements on containers of gas. We measure things like pressure and we measure things like temperature, so forth. All right, but now we also know that as physicists that there is another way to think about this container of gas, and that is from a microscopic viewpoint. So if we think about what's happening in this container of gas on the microscopic level, then what we think of is, rather than just being some like dilute fluid, what we know is that you can think of this gas as being made up of like little balls, right?
Mm-hmm.
And each of these balls has some mass, and they're moving with some speed or some velocity. So this is V1, V2, V3, etc. Okay, so we know that the gas is made up essentially of these little balls. The little balls have mass, they have velocity, and they're going to act like little balls, right? I mean, they're going to hit things and collide with them, and when they collide with them, it's just like a collision from physics 1. You know, the way that you figure out what happens after the collision is that you conserve momentum, you apply Newton's laws of this thing, and in principle, you know, if I know that a molecule has a mass m and a velocity v, and they smacks into another ball of mass m and velocity v, I can predict exactly what's going to happen to every single molecule in this container. All right. So in other words, what we ought to be able to do is, for every ball, so for each atom or molecule, we should be able to apply Newton's laws. Whoops. Okay, and from Newton's laws, we should be able to extract what is the behavior of this container of gas going to be. So now, in principle, we should be able to start out from this microscopic viewpoint where we understand that these things act like billiard balls, analyze them using Newton's laws, and from that extract what this macroscopic behavior is going to be. That is, we should be able, from treating these things as little balls, be able to predict what their pressure and what their temperature and what volume it is that they're going to sit in. Now the problem is that this is extremely hard. Okay, and it's actually really, really easy to see why it's hard. And it's hard essentially because atoms and molecules are so damn tiny. All right, so if you're talking about a macroscopic container of gas, you are talking about, generally speaking, on the order of a mole of atoms and molecules. All right, so on the macroscopic level, okay, so macroscopic level implies that the number of atoms and molecules that you're talking about is on the order of a mole. Okay, and a mole is, that is Avogadro's number. Oh God, how do I spell Avogadro? Avogadro. Let's say it's spelled like that. So a mole is just Avogadro's number of molecules. Okay, and Avogadro's number, that's this Na, And this number is insane, right? This number is, I believe it's 6.022 times 10 to the 23rd. Okay, so a mole of gas molecules is the order of 10 to the 23rd atoms. All right, so now let's think about how we would do this. So let's think about one ball. So here's one gas molecule. Okay, so again, this gas molecule, so let's, for the time being, assume that it's monatomic. That is, we can literally treat it as just a ball. So it has spherical symmetry. We don't have to worry about its orientation. Okay, so if we are thinking about a spherically symmetric monatomic atom or monatomic gas, then in order to describe each one of these atoms, we have to specify several parameters. All right, so we need to specify the mass. That's easy. We just assume that they all have the same mass. But now, inside the box, we need to know where each one of these molecules is. All right, so in other words, for each atom, we need to specify their physical coordinates inside the box. So if this is molecule at number 1, so this is ball number 1, we would need to specify what is its X position, what is its Y position, what is its Z position. Okay, so there's 3 parameters already. But now that's not good enough, right? Because we know that what's going to happen is that these things are all going to smack into each other. And to understand what happens when they smack into each other, what you got to do is conserve momentum. All right, so in other words, you need to know what the momenta of each one of the atoms and molecules is as well. All right, so in addition to their positions, you also need to know their momenta. So you need to know the momentum in the X direction, the momentum in the Y direction, and the momentum in the Z direction. So there's another 3 parameters. Okay? In other words, for each atom in this gas, we have to specify 6 parameters. Okay, so we got 6 parameters per molecule. And we have to do this for every damn atom in the box. Okay, and again, that's 10 to the 23rd atoms. So we are talking 10 to the 24, give or take, parameters in order to fully describe where each atom is in the box and how it's moving. Okay, so we got somewhere on the order of 10 to the 24 parameters. When you set up Newton's laws, you're going to have to set up 10 to the 24 sets of Newton's second law. And then what you have to do is then, numerically integrate Newton's second law every time step for every single one of those equations. Now, at some point in the class, I'm not sure exactly when it's going to happen, but we are going to sit down, we're going to calculate how long would it take to step through 10 to the 24 copies of Newton's second law. That is, in order to perform one time step to see what's going to happen to this gas, how long would it take? And the answer is longer than the age of the universe. All right? So you cannot do it. It is impossible. It is impossible to start with Newton's laws, apply those to a container full of little balls, and from that extract what the macroscopic behavior of the gas is going to be. There's just too damn many. All right, you just can't do it. All right, and so what we're going to do, instead of the brute force method of applying Newton's second law to the 10 to the 23 little balls, we're going to instead apply statistical mechanics. Okay, and what statistical mechanics does is, instead of worrying about where each one of the little atoms and molecules are and what each of their momenta are, what you do is you don't worry about each of the individual ones. You just take the statistics of the collection as a whole. So you do things like calculate averages. So what is the average position? What is the average momentum? What are the deviations away from that average? Okay, so instead of worrying about each individual little ball, you just look at the statistics of the little balls. And from those statistics, you can do things like calculate averages, standard deviations, so on and so forth. And what that allows you to do is to do this, okay? So instead of worrying about each individual little ball, you just look at the statistics. That allows you to start from this microscopic approach. So you start from the microscopic approach, you apply statistical reasoning, okay? And so what allows us to do this is statistical mechanics. Okay, so statistical mechanics is the framework that allows you to start with what you know microscopically about how you expect each one of these little balls to behave. And from that, interpolate how an extremely large collection of those little balls is going to behave. So in particular, if you start out thinking of a gas as a collection of these little balls with mass m and velocity v, and you say, okay, I know if this is true, then they must have some kinetic energy, you know, 1/2 mvi squared. If you assume this and you apply the rules of statistical mechanics, what falls out is this, the ideal gas equation. All right, so at some point in a few lectures, I'm going to show you how you start with assuming you got little balls with kinetic energy 1/2 mv squared, and what you get out of that is the ideal gas equation. It's pretty cool. All right, so does that make sense? Are we good?
Mm-hmm.
Do I have any questions at this point? All right, very good. All right, so again, what we're going to do is apply statistics to large collections of little atoms and molecules, and by applying those statistics, extract what their large system-sized behavior is going to be. All right, so now what we got to do before we can start doing that is to make sure that we're all speaking the same language. That is, so we got to apply statistics. We got to know what the hell statistics is. All right, so we need to lay down some ground rules as to what kind of statistics it is we're going to be calculating and how it is that we're going to calculate it. Okay, so we're going to start off talking about probability. All right, and we're going to start off super basic, and things are just going to snowball from there, okay? So let's say that I'm doing some kind of experiment. So for example, hold on a second, I'll be right back. I got a coin. All right, so now I'm going to do an experiment with this coin. Namely, I'm going to flip it. Boom. Heads. Fantastic. All right, so now that experiment, it has what's called a set of possible outcomes. All right, so the outcomes of your experiment those form a set. Okay? Each element in that set, I am going to call A. Okay? So here's our set of possible outcomes, and that set is composed of all the different kinds of possible outcomes we can have. Okay? So however many outcomes there are, I'm going to call those outcomes A sub I. All right? Does that make sense? So for example, with the coin here, our set of possible outcomes, so here's my coin. I've got frilly 17th century guy hair. My coin, when I flip it, I have two possible outcomes. Heads and tails. All right, so the set of possible outcomes is those two things. And heads, for example, would be outcome A1, and tails would be outcome A2. Make sense? All right, very good. So this is my set S of possible outcomes. These two guys, A1 and A2, are the elements that make up that set. Okay, so now what is probability? So let me write it out for you, and then we'll talk about what it means. So probability is a real valued set function. Okay. That assigns to each event A in the sample set S a number. Okay, so what this looks like is you got your function, which is the probability. It accepts one of these outcomes from your possible set of outcomes, and it gives it a number. All right. Now, I think, so I'm no mathematician, but my understanding is that the way that a mathematician would write this is that they would say that P is a function that takes your set of possible outcomes and maps it into a real number, like so. So I think that's how a mathematician would write this. Okay, so it takes your set of outcomes, maps it into a real number, where these A's are the elements of your set S. So here's the math speak. All right, so now that's what probability is. So probability just takes every possible outcome of your experiment and assigns it a number. All right, now those numbers have to satisfy a few conditions. All right, so now let's talk about what those conditions are that it satisfies. So the following properties are satisfied. All right, so the first one. So probability is always positive. Okay, so probability of anything is always greater than or equal to 0. So it's got to be positive. All right. The second one is that if you're doing an experiment like flipping this coin, and you know what all the possible outcomes are, then the probability of one of those outcomes happening is 100%. Okay. All right, so again, remember S here is the set of all possible outcomes, so that means both heads and tails. So what this says is that if I do the experiment, the probability of getting one of those outcomes is 100%. In other words, something is going to happen that exists in my set of possible outcomes. Does that make sense?
Mm-hmm.
So I wrote this as 100. That's no good. It's 1. So all possible probabilities have to add up to 1. This is what's referred to as probability being normalized. So probability is normalized. Okay, now is when things, so these are both boring. I'm sure you've seen them all before. Now is when things start getting a little bit more interesting. All right, so let's say I have some set of possible outcomes. So those set of outcomes are, let me write it like this. So if my outcomes are, say, A1, A2, A3, so on and so forth, and I look at any two distinct outcomes, that is, so I look at two outcomes where, so look at two events, AI and AJ, where those two events are different. That is, AI is not equal to AJ. No, that's not, I'm sorry, that's not what I meant. I meant I is not equal to J. That is, I'm looking at two separate possibilities.
Mm-hmm.
Then the probability of one of those things happening. So let me write it out in math speak, and then we can talk about exactly what it means. Then the probability of A1, A2, A3, so on and so forth, up to AK, is just the sum of the individual probabilities. Okay, so now what the hell is this thing that I just wrote down here? So this symbol here that looks like a big U. This is, again, this is math speak. This is what's called the union operator. Okay, and the way that you should think about this intuitively is that this is the same thing as like the logical operator OR. All right, so this is the same thing as OR. All right, so in other words, what this equation says is that the probability that I get the outcome A1 or A2 or A3 or A4 is equal to just the sum of the individual probabilities.
Mm-hmm.
Does that make sense? Okay, so in other words, again, if we go back to our coin, so if the coin is fair, then the probability that I get heads is 50%, that is 1/2, and the probability that I get tails is 1/2. So the probability that I get heads or tails is just 1/2 plus 1/2, that is 1. Okay, does that make sense?
Yes.
All right, very good. All right, now, so this is true. If I have these discrete possible outcomes and I want to calculate what is the probability that I get any one of those outcomes, I just take the individual probabilities and I add them up. This is also true even if the set of possible outcomes is infinite. So here I wrote, it goes up to k.
Mm-hmm.
So even if k is infinite, if there's an infinite number of possibilities, this is still true. Okay, so that's that. All right, so now let me give you an example. Whoa, what is that? Oh, I'm sorry. This is from another class. Let me erase this. I taught intro physics last quarter, and my last lecture was over Zoom. So here's the last lecture of my previous Zoom session. So you guys, some of you were kind enough to fill out this survey that I asked you to do about what kind of tech you have available. So none of you guys have virtual reality headsets. I'm so disappointed. We were gonna have like VR chat, we all suit up like Ugandan knuckles and sit around StatMech. I guess that's not gonna happen. Too bad.
Unfortunately not.
Unfortunately, yes. Okay, we're gonna do that later. All right, so let's work through an example. Okay, so let's say we're playing Dungeons and Dragons. All right, and our dungeon master demands that you roll. Oh, somebody is saying something. Let's see what they're saying. Something about Ugandan knuckles. Big brain. All right. Oh, yes. Thank you. Okay. All right. So your dungeon master demands you roll 3 D20 dice. That is 20-sided die. Okay. And get a result. Whoops. Of 15 or higher on all of them. Okay, so you roll D20 die 3 times. The dungeon master says you got to get 15 or higher every single time, or your orc or whatever it is that you're fighting kills you. All right. All right. So let's think about this possibility and ask ourselves a few questions. So for a given roll, so a given die, what is the probability of getting 15?
6 out of 20?
This is out of 20. That's right.
Or 6 out of 20, yeah?
Well, so we're going to get to that. So the first question is, what is the probability to get 15?
Oh, I see.
1
And
out
the
of
next
20.
question is, what's the probability of getting 15 or higher? Okay. And then so each of these questions are for a given dice roll. And then finally, we want to know what's the probability to get a 15 or higher on all 3 rolls. I hope you all can read my chicken scratch.
It's legible to me at least.
What's that?
Legible to me at least.
Legible at least. All right, very good. 15 or higher on
Yeah,
all 3
looks
rolls.
good.
Okay, excellent. Glad to hear it. Okay, so these first 2 questions, we already have enough information to answer, so we're going to go ahead and answer them. And then to answer this last one, we got to talk about one more property of probability. So let's do the first 2 first. All right, so again, our possible outcomes of this experiment. So our set of possible outcomes are that we get a 1 on the die, or a 2, or 3, or 4, or 5, or 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20. Look at that big brain on Brad. Brad being me. Okay, so there's our set of possible outcomes.
Mhm.
Each one of these outcomes is one of the events in this outcome space. All right. So now what the probability does is it takes one of these individual outcomes and then maps it into a real number. So now we got 20 possible outcomes. In principle, if our dungeon master is fair, they're all equally likely. And hence the probability of getting any one of these outcomes is 1 over 20. Okay, so each one of these, what P does is it takes the outcome and maps it into the number 1 over 20. Okay? So in other words, the probability of getting outcome 1, that is a roll of 1, is 1 over 20, which is the probability of getting outcome 2, so on and so forth. All right, so in other words, the probability of getting 15 is just 1 over 20. So that answers the first question. Easy enough, piece of cake. Now the second question asks, what is the probability of getting 15 or higher? All right, so the probability of getting 15 or higher is what is the probability of getting 15? Or 16, or 17, or 18, or 19, or 20. Okay, so to get 15 or higher, you would get one of these outcomes, one or the other. You're not going to get all of them at the same time. So in other words, what we're talking about is this property that we talked about earlier. That to get the probability of getting 15 or higher is you just add up each of the individual probabilities. So this is just 1 over 20. You add it up 1, 2, 3, 4, 5, 6 times. In other words, the probability of getting 15 or higher is 6 out of 20. Make sense? So this is the probability of 15 plus. Good?
Yep.
All right, now, the last thing we're going to talk about today before we're out of time, we're actually essentially out of time already, but we're going to talk about it anyway, is the probability of independent events. So here I'm rolling a die 3 times. And each time I roll it, what I get on that roll does not depend at all on what happened in the previous roll. So each roll is independent of the one that occurs before or after it. All right, so let's say we have 2 events. This would correspond to 2 rolls of our die, column A and B. So events A and B are independent if and only if, okay, and in math speak, they write this as if. Okay, so if I ever write if with two F's, that means if and only if.
Mm-hmm.
So events A and B are independent if and only if the probability of getting A B is equal to P of A times E of B. Okay, this little gizmo here, which you'll notice is the upside down version of the previous operator that we defined. This is what's called the intersection operator. And again, the logic operator that this most closely resembles is AND. All right, so what this says is that the probability of getting A and B is equal to the product of the individual probabilities of each. Okay, so if we have 3 rolls of die, and we want to know what is the probability that we get higher than 15 on each of them, then each roll of the die is an event. Each of those events is independent, and hence the probability of getting higher than 15 on all 3 is just the product of those 3 probabilities. So we already said that for one die, the probability to get 15 plus was 6 out of 20. So for that to happen 3 times, the total probability would be 15 plus times 15 plus times probability of 15 plus. So I just take the probability that each one is 15 or higher, and I just multiply them together. And so the probability of this would be 27 out of 1,000. In other words, you're going to die. It's highly unlikely that you will survive this attack. Okay, now we're out of time. I just want to write down a couple more things, and then we'll be done. Okay, so events are pairwise independent. Okay, so in other words, if I have 3 events, A, B, and C, then they are pairwise independent. So in other words, the probability of getting A and B is the product of A times B. The product of getting A and C is the product of probability of A times the probability of C. And of course, the last one is A, B, and C is just P of B times C. And then the last thing is that for any number of independent random events, the probability to get all 3 of those outcomes is the product of all of them. So again, if I have multiple events, A, B, C, so on and so forth, then the probability that I get all 3 of those at once is just the product of all 3. Okay, if I had 4, then I would just be the product of 4, so on and so forth. So however many independent events you have, the probability of that is just the product of all of them. Okay.
So, Dr. Quick question. So earlier when we were talking about the sum, we said that it held for an infinite set. Does this product property hold as well?
Yes, it does. So this also holds for an infinite set. And so we'll talk about this in more detail in the coming lectures. But you can do infinite sums and infinite products in order to calculate probabilities of infinite sets. Yes. And we'll talk about this in detail. Yes.
Okay.
Okay. All right. So any more questions? All right. Outstanding. So I think we're out of time. So I'll leave it at that, and I'll see you guys on Wednesday, and we'll continue talking about this stuff.
Thank you.
Cool. Thank you.
Thank you.